Okay, hello everyone. Let me turn my microphone. Hi everyone, we're live at this moment. This is December 14, 2017 meetup of our Silicon Valley DLang group. Tonight we're having Jon Degenhardt of eBay, who has been using D to write tools for data processing. And I'm sure he will make a brief announcement about introduction about himself. So tonight's topic is experimenting with link time optimization, and the speaker is Jon Degenhardt. At least we can have. Oh no, not yet. Okay, I'll turn off. So, are we sharing your screen already?
We are.
So.
We're already sharing my screen. Yeah. So.
I mute and please go ahead.
Okay. Yeah. Well, thanks everyone for the coming to or listening to the Silicon Valley D Meetup. I'm Jon Degenhardt. I am from eBay. I work on eBay's search engine. I do both recall and ranking, and I work on search engine components. So I work across both the data science and the runtime search engine stuff. And today I'm going to talk about some experiments I've been doing with link time optimization. Link time optimization is it's available through the LDC compiler. So for anybody who doesn't know, that's the LLVM-based decompiler. And the LDC team has been putting in features of link time optimization since the start of the year, and they've been making a number of releases. It's actually very impressive progress. In the 1.5 release, which I think was in just recently, November, I think, actually a whole bunch of stuff came together to make link time optimization really kind of very, very usable. What's going on? The link time optimization is actually based on the LLVM link time optimization. So essentially what's happening is the LDC guys are making the LLVM link time optimization facilities available in the compiler package. So I'm going to discuss this in the context of these TSV utilities. Now, it's not the only thing I use D for, but it is the thing that we have open sourced, and which they're not particularly exciting tools, but they're actually kind of interesting. They're good for benchmarks. And I'm going to show that we got improved runtimes and smaller executables. And one of my hopes is that by the end of this, that I'll have convinced you to at least pull out the LDC compiler and try the LTO flags and see what happens in your own applications. All right. All right, so first, what is link time optimization? I'm not really going to spend, I'm not going to go into a lot of depth, and it's partly because I only know so much, but so it's really whole program optimizations at link time. And it's interprocedural optimizations that are you really can't do when you're operating on a single file or a single compilation unit. So if you think about the C and C++ and D compilation model, you kind of get a file or you get a couple of files, but for a source file, you produce a .o. And that generally creates machine level code, and that gets optimized at the level of that file. And then the linker comes by later and it grabs all these things and puts them all together, but it's not really rewriting the machine code. So what the idea behind this link time optimization is to postpone generating this machine code until it's got all the code for all these executables together, and then you can get then it can perform optimizations that cross the whole program boundaries. And I think one of the more common optimizations is simply inline expansion, doing a better job of inline expansion. So this is really coming, like I said earlier, this is coming out of the LLVM efforts. It's really, people are doing it for C and C++, but and it's LTO, both GCC and LLVM have LTO capabilities. Now, the LLVM approach, and the GCC approach is somewhat similar, but it's a little different. The LLVM approach to this is the compiler will compile a source file, and when it generates a .o, instead of generating machine code, it puts LLVM's intermediate representation, this IR bit code in, and it puts that in the .o file. So it's actually not machine code in the .o file anymore. And it puts the it puts this in the files, and then the linker comes by later and reads all these files into memory, by the way, which is sort of an issue. But it reads all these files into memory, and then because it's the intermediate representation, it can perform these optimizations to generate the machine code. And that's how LLVM works. GCC uses a similar approach. Now, you might already guess that this requires some changes to the conventional linker. A conventional linker doesn't have any ability to do this. So you need to build these other linkers, and so the way these tend to get written is that the linker has callbacks that it can call into these optimization modules. So on the slides, I'm showing that there are a couple of different linkers that you might use on Mac. It's the system linker Xcode. Xcode supports this in its linker natively. For Linux, you typically use the GNU Gold linker. You can't use the traditional linker, but you use the Gold linker. LLVM also has a brand new linker, LLD, coming out that's being used in places, and so you can use these different linkers, and so you might kind of wonder, well, how can you use the GNU linker in LLVM? Well, they're all just calling these same callback notions. I don't know why it works so smoothly. It's not, I haven't been looking at this, but it does work it seems to work pretty smoothly. And then there are two types of LTO, or link time optimization. One is called full and one is called thin. So full, what it does is the linker reads in the whole IR of your program. Now, the tools I'm going to show the benchmarks on, they're pretty small. Reading in the whole representation is not a big deal. But if you had a much more meaningful size program, you can imagine that reading in all the IR code and then trying to optimize it would actually be a bit of a problem. And in fact, so an awful lot of the work that's been done on LTO over the last 5 years has been to try and reduce the amount of memory and things that the compilers need. Okay, so thin is kind of the LLVM crowd's solution to this. And I think it's really coming out of Google, but it's the LLVM team solution. The .o files hold not only the intermediate representation code, they also hold the summaries of all the different symbols. And so when the linker reads these in, it only stores in memory the summaries, and then it's able to perform its optimization on the summaries. And then when it needs to generate the machine code, it pulls in the actual IR bits that it needs. And so you get dramatically reduced memory times and faster compilation. And it seems like they've managed to retain most of the optimizations that you actually get. So this is what's happening in thin and full. Other thing is they're not compatible with each other. So if you actually try this, you need to kind of pick one and say, I'll build with thin or build with full, and then you need to use that for everything you do. Any questions?
When you say everything, it also loads all the libraries that you use. Can you select and say not those things, but only the my source code? Is that how it works?
Actually, you can, and in fact, that's one of the big things that so you will see. This is actually a theme that you'll see. In the rest of this talk, one of the big things that happened in this 1.5 release is that they now made it easy to actually generate this IR bit code for D runtime and Phobos. So in fact, you can now do this interprocedural optimization across D runtime and Phobos and your own application code, and we will see that's a really big, at least in my programs and my benchmarks, that's actually a big win. and in fact, it's just specifying on the compiler line which libraries you want. So if you have libraries and things like that, you can do that. So and although I haven't needed to do it, I don't see any reason why you couldn't break. If you had a large application consisting of multiple modules, I don't see any reason why you couldn't do the same thing that you can do with druntime and Phobos. So a little brief history of LTO support in LDC. The first version that I wasn't part of any of this. I'm just reading through the release notes. But January of this year, so actually not that long ago, they came out with in LDC 1.1. They had some initial support. It worked kind of on macOS out of the box. Linux, you had to go install extra stuff, things like that. LDC 1.2, 1.3, there were ongoing fixes. LDC 1.4 had two really useful things. First of all, they shipped with the compiler, they shipped the tools you need to make it work on Linux. So if you had, I think it's either Ubuntu 14 or Ubuntu 16, I forget which one, you would, you could run it, you could make it work on Linux out of the box just with the pre-built, binaries that came with it. So you didn't have to go around doing anything extra yourself. It made it really easy. And the other thing they created was this LDC build runtime tool. And what that tool does is, so that's shipped with the distribution. What that tool does is, if you run it, it'll download the source code for the Phobos and druntime libraries specific to that version of LDC, and it will run it, and then it'll allow you to run the compilation of it and generate this IR bit code.
Do other languages have such tools, or is this LDC guy's own effort?
It's the LDC guy's own effort, but so one of the things I think is an interesting question is, suppose you tried to do this with, I think it's interesting, to me it's interesting for other reasons as well. Suppose we will see we get benefits out of doing this for Phobos, which is a template-oriented library. I wonder if you would get the same benefits if you tried to do this with SDL and C++. And somebody here may know the answer to that. You may know that there's a difference in how those libraries are put together. But as I was doing this, I was sort of wondering. But no, the LDC guys are responsible for putting all the tooling together for this stuff. They recognized they could make it work, I guess, without too much trouble, and they figured out how to make it happen. Now, in the 1.4 version, I tried this a bit, and there were still some bugs in it. A lot of the bugs are complicated, by the way, because you're pooling all these different tools together. You've got the C runtime library mixing with a lot of LLVM stuff. The LLVM versions are moving; they're fixing bugs. So this is now LLVM 5.0 is what they're working with. You've got 3 different linkers, and so you put all this stuff together. And I was thankful that I had a pretty solid automated test suite that would detect things for me. And the types of problems I was having were things like you all of a sudden you couldn't catch exceptions, something big. I wasn't seeing subtle bugs. I wasn't seeing that it was making little subtle things. None of that sort of thing went, but you'd have some major failures.
So what kind of constraints does it place upon library use, to follow up on Ali's question? So for instance, you say it works with Phobos. Does it require that you provide the library not in an object form, but obviously in some IR form to work with?
Yeah, so at least for the moment, what you have to do, the reason they download it is that the IR code that gets generated is platform specific. So they didn't want to ship IR code for every platform in the box. So, and I think what they view this tool as sort of a bridge. It was the thing they could put together that works fairly nicely, easily. But,
so you probably want to have the source to work with.
Well, this pulls down the source.
Okay.
And it pulls the source code, and then it compiles it with the IR code. So it makes sure, it's sort of a way for them to guarantee that that you're architecturally consistent without it becoming their responsibility in the binaries. I think if you look at it from the history where they are now, it was a pretty good step. But I think, okay, I can't speak for them because I'm not on the LDC team, but from just talking to conversations, mostly through issues lists and stuff like that, and the Gitter, their Gitter chat room, I get the strong impression that they feel that this is just a step along the way into making this more seamless. And
so I'm guessing that since you probably would need source, that the advantage this would have over a source-based whole program optimizer is that it would probably take less time, but that the source-based whole program optimizer might be able to make faster code since it has access to things at the D level semantic as opposed to just IR stuff. That's a guess. I'm just throwing it out there.
So yeah, I don't know the answer to
Okay.
that. It's hard for me to comment on that. And I need to emphasize, I didn't do any of this work. All I did was try it out. so I tried to learn enough about it to help understand what was going on. But it's really a couple of the people on the LDC team. Johan Engeland in particular is the guy who really did most of this work for the LDC stuff. And so what you'll see in my tools, I did this on Mac OS and Linux. They're also have this in progress on Windows. So I think I haven't followed the status of that. I don't build these tools on Linux, or sorry, in Windows. But I think they're pretty close to having it working on Windows as well. Okay, so a little bit about benchmarks. One of the first things I did, LTO has actually been around for a while. There's, people have been experimenting with it for a decade. One of the first things I did was look around and see, well, what kind of other benchmark results have people been reporting? And to be honest, I didn't find that many. There are really not that many. There are a lot of benchmarks where people are telling you how they improved the compilation, how they reduced the memory that the compiler needs, and how they made the compilation faster. I didn't see, there isn't that much published where people talk about what happened with, with the resulting program, what motivates you to actually do this, to actually use these things. So there's one of the more major ones is a benchmark where people took Firefox and they redid it so that it was using LTO. Now those people kind of concluded that they got some binary size improvement, but they didn't see a lot of runtime improvement. And
I hope they didn't test connecting websites.
And the test struck me as being, well, I have seen some other reports. Actually, they're much more recent, where people are showing, on some standard benchmarks, algorithmic benchmarks, where some things are getting some gains and other things are not. And there's some you'll see in some places that the programs that are likely to benefit are those that have not been highly optimized, and in other words, by hand. So, all right. So, basis for what I'm going to show you are these based on these TSV utilities. This is a set of tools for processing large data files. So think about machine learning data files where tab separated values. You've got, hundreds of thousands or millions of rows of data. Often they're floating point numbers, but they may be textual values and things like that. Not so big that you would need to go to a distributed system like Hadoop or Spark, but something big enough that you somewhat care that it performs. So I wrote these as I built these as an exercise exploring D when I was starting to program in D. And one very nice thing about them is that there are a number of other tools out there that do something very similar. And so you could actually get some benchmark comparisons. And I produced a benchmark comparison in March of this year. And so one of the takeaways that you should come away, I'm going to show you the main benchmark comparison. One of the key takeaways I'd like to suggest, though, although when I wrote these tools, I wrote them using Phobos, the standard library. I did not go do my own buffer management or go do low-level stuff. I did not write it as if it was a C program. I used the garbage collector. I used all these things. My goal was to see what would happen if you had sort of a large group of people who were programming, and it's not like I purposely let them be slow. I mean, I took some pains to make sure I wasn't doing things like unnecessarily allocating memory and things like that. But that's about as far as it went. And these tools, then I compared these tools to a number of other tools that are out there, and actually they did pretty well in the benchmark. So so this is from the March 2017 benchmark, and this is so these are things where I was able to find other open source. I have quite a few more. The tools do quite a bit more than this, but these are places I was able to find comparative benchmarks, both in traditional Unix tools like cut, for example, or awk, and also a number of open source tools, all written in native programming languages like C, Rust, Go. So the tools in this toolkit are all the ones on the left. In other words, these tools were the fastest on all these benchmarks. And so,
can you remind us of the
problems? Yeah. So like I was mentioning, you've got these tab-separated value files that have large numbers of rows, and the different types of things they do. Okay, so the first one is a very traditional thing where you have comma-separated value files, the way often gets produced by databases, especially, Microsoft databases will produce a CSV file. So this is just this is a conversion, and it walks everything, and it converts them. And what's really doing is it's processing the CSV escape format. CSV allows you to put, it's a comma delimited, but it allows you to put commas and other sorts of special characters and carry returns in, and so you have to convert that. Summary statistics is things like mean, average, median, that sort of thing. Is so traditional summary, really summary description statistics, and you would say, tell me the min and max and the median, or the of columns, or 3, 7, and 19, something like that. So this is one of the, and a number of toolkits do this. One is that's somewhat popular is GNU Data Mesh. That's a tool written in C. In these, because a lot of these toolkits are written by clearly one or two people, mostly, I didn't feel like bashing people, so I anonymized the toolkits. But if you actually want to go find out which toolkits did what, the information for reproducing the benchmarks is all on the site, and you can run them and find out. One of these is GNU Data Mesh, and for this summarized thing. Numeric row filter, this is about saying, well, I want to find all the rows where, say, column 3 is greater than 5 and less than 10, or column 5 and column 6 are within a delta of each other, or that sort of thing. So numeric filters is exactly that, and very often what you're doing is you're converting strings to numbers and performing these numeric comparisons. Regex row filter is very similar, except it's regular expressions, and it's using the D regular expression library to do that. I didn't handle regular expressions, I just used the library. Column selection is just cut. It's the traditional Unix cut, except that you can reorder the columns, but other than that, it's just cut. Join is basically a relational database style join, but it's
So why is TSV faster?
Why is it faster? That's actually a good question. To be honest, I think it says something in a lot of these cases about the other tools more than it does about these. I had when this happened, by the way, I was completely shocked that it was first in all these metrics. I did not expect that. I couldn't believe it was faster than a Unix tool like cut that's been around for, I don't know, what, 30, 40 years, and been optimized. And Mock is a version of awk that's been, it was highly optimized. Now, Mock is, one thing to realize is a lot of these tools are doing different things. Some of the specialty toolkits support CSV primarily, and so if you're trying to support both TSV and CSV dealing with escapes, it's hard to make TSV really, really fast if you're also supporting CSV at the same time. But that doesn't say why GNU Data Mesh, which is pretty new, is quite a bit slower, which I had trouble believing that well, it doesn't say why cut is slower. It doesn't say whether these other things are slower. So to be honest, I don't know. But I think it's actually says something pretty good for for D. So
And if I'm not mistaken, you said one of these tools got faster after you published your results.
Yes, actually, the Rust toolkit. The guy looked at these and he said, okay, and he went back and he made his CSV to TSV time. Actually, I reported the CSV to TSV times. So those were the tools where it was most competitive, and at one time in my benchmarks or all those 3 tools were the fastest. At the time I actually did the March benchmark, my tool was the fastest. The Rust guy's tool, I think, is now faster actually than mine. But
how much faster?
What's that?
How much faster?
I'm not sure. He benchmarked it himself and put it on one of the issues pages. If you go look at the issues on the GitHub, you can go find all his comments.
And there was some fun discussion on Reddit actually when this came up, and then the other people said, "Wait, so now we beat it." There was a response blog post, I think, after yours. So there was some fun discussion there.
Yeah, there was right. So there was so I think one thing to realize is none of these tools is 100% as optimal as they could be, right? So if somebody wants to go out and beat these tools, you should be able to do it.
But there should be like a rough correlation. You should look at the code, say, is this relatively clear? If I know the language, I mean, obviously, if you look at a language you don't know and just poo-poo it, that's ridiculous. But if they're roughly the same size, that should tell you something.
Yeah. So the key thing is, so this is the March benchmarks. No LTO in this at all. I'm going to show you what happens to these numbers when I start using LTO, so the other thing, the drum roll. So there's the next slide. Yeah.
Is this using just the standard Phobos, or are you using things like IO pipe?
No, I for my own stuff, I wanted to use only things which came out of standard Phobos, not even experimental.
Okay.
Yeah, I did work with Stephen on trying IO pipe out on this, and actually IO pipe made these faster. Actually, we tried it on TSV filter, I think, which is actually one of the fastest tools I have, and he's made it a little bit faster. So yeah, I'm hoping. But the reason I have that, because I work for a big company, I wanted to use things which are in the standard library, so that was part of the evaluation idea. Okay, so I think you'd all agree though, this doesn't suggest that there's like this huge amount of open stuff for the for the compilers to go after. In other words, you're not just making huge corrections to bad mistakes by the programmer. So that's a sort of a thing. So this is what happened. So this is results with LTO. This is macOS. Now I know this chart is a little bit has a lot of rows, and unfortunately there's something I've got. There's a little complication with the benchmarks I've got to describe, which is so these benchmarks were done. The benchmarks I showed you in the previous slide were done with LDC 1.2, which is the top row. No link time optimization, because frankly I'd never tried it at that point. Now, there was something that happened though in LDC 1.3, which is that LDC suffered some regressions in its ability to optimize some of this code, and I think it was actually its ability to optimize across my application in Phobos. And so for quite a while now. Is this saying? Oh, that's on me? Okay. Okay, great. We're not muted. I was afraid all of a sudden we were muted. Actually, because of this, in the pre-built binaries that I put of this code on the GitHub repository, I've been using LDC 1.2 and skipping 1.3 and 1.4 because it actually made these tools slower. And you will, if you go to some of the LDC issues, you may see some long, one in particular, one very long, issues discussion where we tried to track down what was going on, where I was working with the LDC guys to try and figure out what's going on. And looks like it's something really complicated. And at one point they said, you know, I think I think when we have link time optimization for Phobos and D runtime, I think this problem will take care of this problem. So they decided that they wanted to actually concentrate on that, not try and figure out, you know, what was happening in regression. And it's not just something that might happen in the D compiler, but also Phobos and and D runtime are changing. And it sounded like to me there were a bunch of magic parameters that they were using to tune some of how they made decisions about template instantiation in the runtime that was interfering with inlining, inlining of templates. And it seemed like that was what was going on. By the way, in the type of apps that these are developing, one characteristic of them is that they tend to get in a very tight loop where they're reading stuff in and they're performing a loop. And as soon as you make a mistake in that loop, it starts to show up with some magnitude. So that's why it bubbles up to the surface in this kind of application. It would happen in other types of streaming applications or other things where you're just processing, doing data processing. It need not be just in files, but if you were like Kafka queues or something like that, where, it would happen. So we have LDC 1.2. Now you get kind of two choices. In LDC 1.2, you could run things, run the stuff on it. You could do this on the application code you could run LTO on the application code. D runtime and Phobos were still just using, the normal compilation. That's if you use the out-of-the-box solutions, which was what I was doing. And you could see in the CSV to TSV, we got an improvement. Everything else kind of really stayed pretty much the same, pretty minor changes. Now LDC 1.5 came around. You see, actually, it's actually improved over 1.2 in the CSV to TSV, but most of the others actually suffered that regression still. And then if you look at the app thin and full, so what thin is obviously using thin LTO, full is using full LTO, app is just the application code. And you really see that you don't actually get that much of a delta. It doesn't really look like it's worth doing just to do it against the application code. Now my apps are pretty small. If you had a really big application, that might not be true. But then the last line there, the LDC 1.5 with the dlibs, that means I ran LTO against Phobos and D runtime and my application. All of a sudden, you start to see these somewhat material improvements. In fact, most of these are getting quite a bit faster, and not just faster than the 1.5, but faster than the original, LDC 1.2s.
How is compilation time affected?
So my apps are probably not the best benchmark for compilation time because they're relatively small. Yeah, it is slower. At one point, for the LDC guys asked me, and I generated some numbers. So it's a little bit slower, but on my apps, it's really not a problem. I think the real thing would be to benchmark that notion on a much larger application, because I also don't think it's linear. I think I get the impression that as your app scales up in size, you get a little bit of a compounding effect as you start to hit memory limitations. But
yeah, it tends to be true of whole program optimization too.
Yeah, but really, this is really some pretty remarkable numbers on. We're seeing not every app got improvement. TSV Select, which is essentially cut, really saw no delta. So TSV Join is doesn't really see any deltas either. TSV Join is really dominated by generating a huge hash table, and these huge hash tables in D run into a lot of memory and garbage collection considerations at the moment. I think it'd actually be, if we eventually get a hash table update that's actually a little bit more memory friendly for very, very large hash tables. By large hash tables, I mean 8 million elements. This sort of, I don't mean something small. I mean something really big. So TSV Join is dominated by that, and there doesn't really seem to be anything you can do to materially improve it without improving the hash table. But these other apps are really getting, some pretty decent improvements.
Have you try. So I don't know how big 8 million is in terms of RAM store, like how many gigabytes it is, but is it small enough that you could just turn GC off?
Well, you probably could, and in fact, in a number of these apps, one of the things that's happening is, oh well, with TSUV join, well, it fits in. Okay, so I ran these benchmarks on this laptop, which is a 16 GB. For those file sizes, I could, but the goal was to be able to handle, pretty large files, and so,
Sure.
I mean, yeah, you might be able to do that. I mean, for TSV join, if I really wanted it to be dramatically faster than it is, I'd just write my own hash table.
So I was
What I
thinking
would do.
that then you wouldn't be able to use the D built-in associative arrays, right?
Yeah, that's what I'm using,
Sure.
right? But my goal in this is,
Totally
okay,
agree, yeah.
I mean, these are real tools. That's one of the nice things, and I really use them, and I really use them on files this large and larger. But the reality is, for the things I do and my colleagues do on a normal everyday basis, they're plenty fast. Once we've got here, these are fast enough. I don't need to go around writing a new hash table or play around with the GC. So I'm more interested in understanding, how the capabilities of the language that we might see in using it. So this is on the Mac. If we look at, so this is the results on Linux, and again, we're seeing in the same set of programs, we're seeing pretty material speedups. Now, this Linux box is actually a lot slower than the Mac here. It's a commodity cloud machine. So that's why these runtimes are quite a bit slower, or I think that's why. But it kind of makes sense. So it's sort of a box I had some access to, and still, though, we're seeing, 20, 10 to up to 30, percent improvements, and that's over the 1.2 version. Over the current 1.5 version, again, we're seeing, in some of these tools, pretty big numbers. Not every tool, but pretty big numbers. And this is just from, do anything with the code. So I thought this is actually pretty remarkable.
So regressions make people happier, apparently. Good thing they regress, so you have bigger numbers now.
Well, you notice that I am reporting the delta from 1.2, which is, I think, maybe, both the delta from 1.2 and the delta from 1.5 in both of these benchmarks. So the last two, that's what the last two numbers are. That's me trying to be the data scientist and not the marketing guy. The marketing guy wouldn't have told you about 1.2 and would have just said, LDC is really fast, here's 1.5. But I'm a data scientist and I'm supposed to try and do objective evaluations. So hopefully, and just again with the Mac OS stuff, you see again, from the 1.2, which is a very nice benchmark, you're still seeing numbers 10 to 30%. These are bigger numbers, by the way, than any other I've seen reported. So they might be special to this app. They might be special to the way the decompiler works. Is what you can also see why I was saying I think it would be really interesting to try something similar in the seed land with STL. If you could, I don't know if STL has the same kind of issues with trying to do inlining or not.
Yeah, I'm guessing templatized code will not benefit that much. I don't know.
But Phobos is a template-oriented library too.
Oh, I see. Maybe they reduce the memory footprint.
Well,
stuff gets complicated.
Yeah, and so a conversation with some of the LDC guys who are implementing this stuff might actually shed a lot of light on this. I got the impression talking to them that what's really going on is that they're making decisions about when to instantiate a template and effectively turning it into a function, and then reuse that across the whole application. And that's happening sometimes when they're doing the compilation of the Phobos library. I have no idea if that happens at all in C++ land, but it's still a template that you're deciding to instantiate. It's just that Phobos is calling. Well, you have one Phobos thing calling another, I guess. I'm not sure. Or I'm not sure. I don't really understand that chain of interactions, because I was very surprised to find out that was happening. But it sounds like it is. So
at least according to just looking it up on the web, Rust since October has thin link time optimization. So that might be a comparison too, since somebody wrote the competitive library. See how well they did.
Yeah. So let's look at executable sizes. So this is Mac OS, and now here I just recorded the delta from 1.5. Mac OS on the top, Linux on the bottom. So the Mac OS binaries are actually pretty big to start with, much bigger than the Linux binaries. Now Mac OS does use dynamic linking for its equivalent of libc. So it's not that it's statically linking libc or anything. Does anybody know why the starting binaries are so big? Bigger, but on the Mac, we're knocking down these. We're knocking off 60% of the of the binary size. That's really quite remarkable. It'll be interesting to see how that held up against other apps. On the Linux side, we're not knocking off as much, but we're still knocking off 17, 18% typically off the binary size. Now, one thing I'll point out, this is something Jon Degenhardt described to me. One of the reasons that it's able to make these optimizations, so people will talk about things like it can do better dead code elimination. Well, what's happening in the LTO land is that it actually has all the symbols. So it's not just doing dead code elimination, it's actually dropping out all unused symbols. So whether it, and so like on the Mac OS piece, I took one of the executables, I forget which one. I ran nm, which will tell you the number of symbols. I think I did it on TSV Filter or TSV Summarize, which are two of the bigger applications. They go from, the one I ran it on went from something like 17,000 symbols to 7,000 symbols, just in the, in what's in the actual built binary. So that's actually, so it's really dropping individual pieces. So that's really quite amazing. So that's that on that front. So
actually, quick question about that table. You've got the app both for thin and full, and then you have dlibs for thin. Do you have the dlibs and your app for full?
And actually, I think on the Linux one, it should be full. Okay, so one of the things that's going on here, which I meant to describe earlier.
Well, both of them for the dlibs say thin.
They say thin. I think the Linux one should say full.
Okay.
I think that's a mistake in the slide. So what's going on here is that it turns out that in the current implementation of all this stuff, that if you put all this stuff together, well, thin and full work on your app code. If you on the Mac, if you use full on everything, there's trouble. But thin works fine, at least on my apps. If on Linux, it's the opposite. So on Linux, full works completely fine, but I had trouble with thin, which is why I know the bottom line is wrong. So so there are some they're all in the LDC issues list. So I guess what I would say is, don't go out and take your critical production needs app and send it through all this stuff yet. But if you have things that you can try it on that you have good test suites for, and I have pretty good test suites, which I was thankful I had. And like I said, when I had errors, they were big errors, like it failed to link, that sort of error, or there was one that was a little bit more subtle, but it wouldn't catch runtime exceptions, and that occurred when I was using Ubuntu 14 with static linked libc and that sort of stuff. So there are all these tools are the ecosystem for these tools are just really getting everything together. So it's still, despite that LTO has been around for a while, like almost 10 years, I think people started experimenting with it, or 7 years at least. it's still the getting all these ecosystems together, especially if you're going to build on multiple platforms, is still just coming together. So yes, nice catch on that. So I thought maybe we would actually try to build something and just try to do it. So I said one of my goals was to convince you should try it. So I thought maybe we would try it and just see how it worked. But first, let's go. I'm going to use. So there was a blog post I did earlier this year called Faster Command Line Tools in D. I'm going to take one of the sample code that I did use there, and I'm going to build it. The build line for no LTO is just going to be LC2 minus release minus O, and build the build it with using LTO in its completely full form. You just do this you just run the build runtime tool first. You actually don't need that reset flag if you're doing it initially. You tell it whether you want to use thin or full, which is what's in there, and then you run your regular build command, and you for your code, and you say that you want to use LTO thin, and then you give it the a link to the runtime libraries that you just built, and that's what you do, and that's what you did. So I think we will try this and see if we can make this work.
Does Dub support these arguments yet, or?
I haven't tried using it in Dub. I'm just building it in my make files at the moment, and Dub might support it. I have a feeling you're going to end up writing some script-like things. I didn't bother, frankly, but if enough people try to use it, I have no doubt that it'll get incorporated into Dub. So first, let's just take a look at what this code looks like, just so you can sort of see it. It's not a big program. What this program does, it's another one of these command line tools. It takes a data file. It's actually this. I'm going to give it the Google Ngrams file, and what it's going to do, the first column in the Google Ngrams file is an ngram, like a word, a term, and the other columns are things like the year, so like 1990, the number of times Google found it in the documents there. It's a Google Books project, so the number of times the term occurred and the number of books it occurred in. So it's essentially a TF-IDF sort of measure, and then so I'll run a command to do something like aggregate across the across all the years. So in other words, if you had a term like Apple, and then you find it's got 400 years of data, maybe you want to aggregate all those together. So that's essentially what this little program does. And it's, like I said, it's a pretty small little program. So it's not very big. Okay, so let's actually do this, and I'm going to cheat a bit on my commands. So let's build a. We're going to build a. I didn't get that completely. We're going to build a no LTO version. Okay. Now we will build a. Now I'm going to build the runtime. We'll try the runtime link stuff. Get rid of this, so it's actually going to start out by trying to find this the source code. Is this readable? Should I make the font bigger? So it's actually just pulling in all. It's just pulling in all the source code, and now it's going to actually compile it. And so this is now compiling D runtime in Phobos.
So it's going to take like 1 hour or so.
If it was going to take that long, I wouldn't do it in front of you. I would have had it pre-built.
So are you telling me D runtime and Phobos builds less than an hour? I'm just kidding. I know how fast it is.
Yeah, there's
A little bit of marketing there.
Yeah, Ali is not the marketing person either. Okay, so it's done.
Wow.
All right. So now actually we get to build our second version of the program. Now you might, if we had timed the compilation, you will notice that this is took just a little bit longer. Now it was a small program, but it was doing the compilation. So if we do something like this, we will see. What did I? Oh, I shouldn't have done that. Let's see. Okay, so these are our two binaries. You'll see that the bytes of the, this is not too much more than a hello world app, except that it is using a number of Phobos facilities. And you'll see that we're about a third of the size of the binary. Let's see. So let's see. So we have this entagrams file. See, this file is not. Oh, it's a link. That's why it's small. So it's about 10 million lines. They're not big lines. It's about, I think it's like 280 megabytes, something like that. Just show you what it looks like, just so you get the idea. So it's got a whole bunch of things like this. So the first term that it's looking at, this is one of the first files, and it's looking at terms that start with the letter 0. So where's the digit 0? So it's just got a long set of these things. So now, if you really want to find out what the program is doing, you can go back and look at the blog post. But what I'm going to do is I'm just going to run this a few times, first with the no LTO version, and this is exactly what was in the blog post. So you can see it's about 1.21 seconds. It's actually it's not it's a lot of rows, but it's and the max key, that's the value, that's the result of the program, by the way. So it's okay. So this program was already, it's a pretty small program, already pretty fast. If we ran this a bunch more times, that delta between 1.2 and 1.1, that would hold up, right? So okay, so that was a minor program. It was probably not worth doing it for that, but you can it just sort of gives you the idea. And it's just really trying to show that it's really, it's really very tractable to try and build this. And now I haven't needed to try and do it, but if you had a much larger program or you had, .o files, you could see it was just what it had to do for Phobos and things. I'm sure it would take a little bit more setup, but anything you could do with that Phobos source code, you could do with your own source code. So, okay. Any questions about that? Does that seem easier than you thought it might be? Okay.
General question: how easy is building LDC? Do I need to go through many steps?
Well, so Okay, these are the the pre-built binaries. I just installed the pre-built binaries. I have built LDC any number of times. Actually, if you read your instructions carefully, it actually works pretty well. But no, you don't have to build LDC yourself. You just use the pre-built binaries. Okay, so let's go back to the slideshow. Okay, so almost done. Some concluding remarks. First, I really need to make some acknowledgments to the LDC team, the whole LDC team, but especially Johan Engeland and Martin Kinklin. If you go look through some of the issues, you will see that they had some long discussions, on some of these problems. They helped me figure out how to set some of this stuff up, and despite that, a couple times I threw at them especially some of these performance regression bugs. Frankly, I'm sure it was a real nuisance for them, and I never got anything but encouragement and thanks for bringing it up. And so these guys really did, really helped out a lot, and it's really their work. I'm just showing off what kind of they did. To me, LTO, now that we have the 1.5 release out, it looks like it's really an option to start working with. Yes, it's still early. There are still bugs. There are still problems that are being worked out, and not just in the LDC team, but also in the LVM team. But it's really at a very promising stage. Okay, the other obvious one, we saw big improvements on the TSV utility apps. It's not completely clear all the optimizations that are being applied, but I think the big one is just cross-module inlining. Is really what's happening. We're getting a lot more cross-module inlining. Other types of apps will have bigger issues with compilation times and things like that. The thing you and I were talking about earlier, this is just one type of benchmark. Although that's, I ran these on a bunch of different tools, they're all still following a similar pattern. Now, I will say that the tools themselves use a bigger variety of Phobos things than you want. Like TS3 Summarize uses a class architecture, so it's doing a lot of, it really has classes and instances, and that's because all the operators like sum and median and things like that are all represented as classes. The CSV to TSV uses a hand-rolled state machine with gotos. The TSV filter is using vectors of delegates, and it's evaluating vectors of delegates. There's a fair number of Phobos library types of things used, more than you might expect. So despite that you might think that each of these tools is just a minor variant of each other, they're actually using a fair number of both techniques and Phobos library things, but they are still a similar pattern. So it'd be really great to get some other types of applications to try this and see if other people see similar benefits. Profile guided optimization is the next thing to try. So profile guided optimization is where you run essentially samples, and you tell the compiler to instrument the samples, and then it does further optimization. So when I wrote these slides up 2 weeks ago, I hadn't tried it. A few days ago, I actually tried it on a couple of the apps, and no, this is only on Mac, and I need to do more work on it, but on TSV Summarize, I got another 10%. Wow. And yes. Now, the couple of the others, I was getting more like 3 to 5%. TSV Filter, I got 3 to 5%. CSV to TSV, I got nothing. Now I'm guessing with the TSV Summarize and TSV Filter, they're also the biggest apps, and they have a large amount of runtime setup. So they sit around, and one of the reasons they're fast is that you initialize a lot of data structures, and there's actually a lot of code there. So profile guided optimization was probably able to tell it, hey, don't spend any time optimizing. If you're going to pick and choose where to optimize and where to do inlining. Don't do it in this setup code. Do it in the stuff happening in these tight loops. I'm not sure about that, but that's my hypothesis. But anyway, we got gains. Similar though with I tried profile guided optimization. I think earlier this year without LTO, and I saw nothing. Right, so this combination of doing stuff across the app and Phobos and deep runtime seems to be a really promising thing. It's made me wonder if you could do something similar with libc, because one of the things that Johan Engeland in his blog, he has a blog post that he wrote about a year ago about this stuff, said that LVM doesn't care one bit about whether the original source code was D or C. It just gets this IR code, and it can actually start to optimize the IR code together too. So there's really nothing that says that you couldn't take C libraries at the source code level and plug them into the same optimization framework and get optimization across. So the only other thing is a bunch of references. I'll point out some. So there's a number of things that you'll find on largely in the LDC part of the DLang site. There's actually, if you really want to understand LTO, there's this talk. It's the third bullet from the bottom: thin LTO, scalable and incremental link time optimization. That was at CPPCon just a few months ago. It's about an hour talk. It's on YouTube. It's Teresa Johnson is from Google, and she's describing thin LTO as it exists in LLVM. It's actually a fantastic talk, despite that it's about thin LTO. If you want to understand how LTO works and what its current status in the world, that's really the talk to see. So questions?
Not from you. This is the end of this broadcast. Thank you very much,
Okay.
John. That was awesome. Thank you.